Hey everybody, welcome to the reduction of a ketone lab. Here's the outline for this video. I'll be going over the reaction and the mechanism briefly. Then I'll go through the procedure, talking about gas chromatography as well. Then I'll show the experiment in the lab. And at the end, I'll spend a good amount of time talking about topicity and how that applies to NMR. Here's the reaction that we'll be doing. We'll be taking cyclohexanone and reducing it using sodium borohydride to form cyclohexanol, which we can also show in the chair conformer, which will be more important when we talk about topicity and NMR. Here's a quick look at the mechanism. The borohydride complex will react with the ketone, donating a hydride to reduce the ketone eventually into an alcohol, and it forms this intermediate. And notice that the borohydride compound has 3 additional hydrides that it can donate, so it'll react with 3 additional ketones to form the boron complex intermediate. Then, as that complex interacts with water, cyclohexanol is formed, and again, there are 3 more molecules attached to the boron, so this reaction will happen 3 more times to form an additional 3 cyclohexanol molecules, for a total of 4 cyclohexanol products per borohydride compound. So when we look at the table, we might think initially that sodium borohydride is the limiting reagent because it has a smaller amount of millimoles, but in reality, cyclohexanone will be used up 4 times as quickly, so that'll be our limiting reagent. Now, a little bit about the reducing reagent, the sodium borohydride. It's a fairly mild one. It's milder than other reducing agents like lithium aluminum hydride, so it's good for reducing aldehydes and ketones. And it reacts really well in a methanol solution, so that's what we'll be using, and we'll dispense it with a needle and a syringe in the hood. Once that's added to the cyclohexanone, we'll let it react at room temperature for an hour, and that'll be in a conical vial with an air condenser attached. Once that hour has passed, a little bit of hydrochloric acid will be added to react with any sodium borohydride left over, as well as to neutralize the sodium methoxide from the methanol solution. Then we'll extract that solution 3 times using methylene chloride, which is a common organic solvent used in the lab. There is a slight safety concern with methylene chloride just because it is a probable carcinogen, but there shouldn't be any issues as long as it's handled with care. Methylene chloride is more dense than water, so when it's added to the conical vial, the bottom layer will be the organic methylene chloride solution. Then, as those 2 layers are mixed together really well, the cyclohexanol product will move into the organic layer, and we'll do this a total of 3 times to make sure that we extract as much product out as possible. The extracts will be dried with sodium sulfate, which will be added until it's free-flowing, and after the dry methylene chloride solution is removed, we'll rinse the sodium sulfate with a little additional methylene chloride to help reclaim any product that would have been left behind or would have been kind of trapped within the sodium sulfate. We can then evaporate off the solvent in a conical vial using a gentle stream of air and gentle heating, being careful not to evaporate the cyclohexanol off as well. This shouldn't be an issue because the boiling point of cyclohexanol is 161 degrees Celsius, but to be safe, we'll use gentle heating to make sure that doesn't happen, and because it doesn't take a lot of heat to evaporate methylene chloride. Once the solvent has been fully evaporated off, we can weigh the remaining liquid product to calculate a % yield. And then we're actually going to correct that yield using gas chromatography because it's likely that we have some contamination with the product. For example, here's our conical vial with the liquid product in it, but it's possible that there is still some unreacted cyclohexanone in there, and maybe even some methylene chloride if it wasn't completely evaporated. So the % yield that would be calculated from the remaining liquid in the conical vial wouldn't be accurate. It would be artificially high because there are more things in there than just the product. And this is where gas chromatography is useful because it can separate the contamination from the product, plus it can tell us how much of each compound was in the liquid that was introduced into the chromatograph. We actually won't be running our own gas chromatography, but there are examples in the procedure that we'll be using, so here's a diagram of how that works. The sample is injected into the chromatograph, which is basically a mini oven with a column inside. So the compounds are turned into a gas, and those gases are run through the column, which can have a polar or nonpolar packing depending on how we want to separate the compounds. If there's a polar packing in the column, then more polar compounds will be retained longer because they'll want to interact more with the column. If it's a nonpolar packing, then nonpolar compounds will be retained longer. Then a carrier gas is used to push the compounds through the column, so this would be the mobile phase, and oftentimes helium or nitrogen gas is used for this. As the compounds come out of the column, they'll be picked up by a detector, and then a computer will analyze the data, giving us a printout of peaks showing us the retention time of each compound, and the area under each peak will tell us how much of each compound was in there. This is an example of what those printouts look like. On the x-axis we have the retention time in minutes, and then the peaks for each compound that was run through the column. The first one we see is methanol, so that came out first, and then a little bit later was ethanol, and then even a little bit later was isopropanol. So this had to have been a nonpolar column because the more polar compounds came out first, and then the less polar ones were retained longer. Now let's talk about how we would correct the percent yield using this as an example. Let's say that we did evaporate all of the methylene chloride, so unreacted cyclohexanone would be the only thing contaminating the product. And let's say that we calculated a percent yield of 56%. This sample was run through a chromatograph, and this is the printout that was given for that sample. The first tall peak would be for the carrier gas, so we don't really care about that, but the remaining peaks would be for the two compounds in the sample. To know which peak goes to which molecule, references could be run with standards to know when each compound came out of the column. So this reference was run for cyclohexanone, and it had a retention time of around 2.9 minutes, whereas this reference was run for cyclohexanol, and it had a retention time of around 7.2 minutes. That means that this smaller peak with a retention time of around 2.9 would be for cyclohexanone, and the larger peak with a retention time around 7.2 would be for cyclohexanol. From this, we also know that the packing in the column was a polar packing because the more polar cyclohexanol was retained in the column longer. From here, we'll be using this table to correct the percent yield. In the first column, we have the retention times. So again, the first two we don't care about because those are pertaining to the carrier gas, but the bottom two are for our actual compounds. And in the second column, we are given the areas under each peak, which is what we'll be using to correct the yield. Using the areas, we can create a ratio of how much product was in the total liquid sample that was introduced into the chromatograph. So we only care about these two areas, and what we'll do is take the area of the product peak, which would be this number, and divide it by the total area of both peaks, which would be these two numbers added together. Then we'll take that ratio and multiply it by our original percent yield to get a corrected yield of 54%. So in this example, there wasn't a whole lot of contamination because the percent yield didn't change that much, but it can change more drastically depending on the data received from the chromatograph. So here's a student sample found in the procedure, and there are a couple to choose from, but we're going to correct the percent yield calculated from the actual experiment using the data found on one of those. And we'll set up the equation the exact same way. The peaks have already been labeled for us, telling us which compound goes to which peak, and only the pertinent peaks are shown here. We are also given the retention time and the area for each peak as well. And finally, at the end of the experiment, we'll characterize the product by running an IR spec. Alright, I'm going to add 100 microliters of cyclohexanone to a 5 milliliter conical vial with a large spin vane. Then I'll be using a needle and syringe to dispense the sodium borohydride, which comes in this packaging. So I'll open up the packaging and attach the needle, which is just held on by friction. And then taking off the lid is where students often poke themselves, so I'll just use my thumb to gently press off the lid. I'll be dispensing 300 microliters of sodium borohydride, and to equalize the pressure, I'll want to add about the same amount of air as reagent being taken out. So initially, I'll inject the air, then dispense the 300 microliters, and afterwards, to make sure I don't poke anyone, I'll gently place the lid on top. That can be added to the cyclohexanone, and then I'll set up the apparatus, attaching the air condenser to the top of the conical vial. And now I'll just let that react for an hour at room temperature. While that's going, I'll dispose the needle into this container, which is just for needles, so I'll separate it from the syringe, tossing the needle into the container, and then I can throw the syringe in the garbage. After the hour reaction is done, I'll remove the air condenser and take the conical vial over to the hood, where I'll be adding about a milliliter of 3 molar hydrochloric acid. Then I'll get some methylene chloride in a beaker to perform the 3 extractions, and I'll make sure to mix the layers really well to extract as much product from that aqueous methanol solution as possible, combining all of the extracts into a separate Erlenmeyer flask. Once the extractions are completed, I'll dry the methylene chloride solution with some sodium sulfate, adding it until it's free-flowing. Then I'll remove the solution from the sodium sulfate and rinse it once with some additional methylene chloride to reclaim more product that might have been left behind. I'll evaporate the solvent on the hot plate so it can be gently heated, and I'll be using the vinyl tubing from the drawer to introduce a gentle stream of air as well. That tubing can be attached to the lab air valve, and as I turn it on, I'm going to check with my hand to make sure that it is a gentle stream of air, because I don't want to blast all of the solution out of the conical vial. I can use a clamp to hold the tubing above the conical vial and start evaporating the methylene chloride off. I'll let this go until the level of the liquid stops going down and the side of the glass is no longer cold to touch. At that point, the methylene chloride should be all gone and the product can be characterized. I'll first weigh the full conical vial so a % yield can be calculated, and don't forget to correct that yield using the gas chromatography handouts in your procedure. Then I'll spot the salt plates using an open capillary tube and place it into the spectrometer. And it doesn't look too bad. We can clearly see the alcohol peak, plus a peak around 1067 for the carbon-oxygen bond. And it looks like there's a small carbonyl peak around 1700, so there must be some contamination from cyclohexanone, but it looks pretty small. And finally, at the end, I'll weigh out the empty conical vial. For this last portion, I wanted to spend a good amount of time talking about topicity, discussing things like diastereotopic hydrogens versus enantiotopic hydrogens, and how those will affect the signals that we see on NMR. This tends to be a source of confusion for a lot of students that take this class, but if you feel comfortable with these concepts, feel free to put the video on 1.5 speed or something, because I'm going to be going through this pretty thoroughly. Before we even start analyzing the peaks, let's take a look at the two compounds and identify how many unique hydrogens would be on each one. For cyclohexanone, we can look at the 2 hydrogens attached to this carbon and see that they're equivalent, so we'll label those as A. And then the hydrogens on the opposite side would be the same, so we don't really have to label those. Then just going down the molecule, these 2 hydrogens would be equivalent, so we'll label those as B. And the bottom 2 hydrogens would be equivalent, so we'll label those as C. Now we can take a look at cyclohexanol and do the same thing. We can start with the hydrogen attached to the alcohol group, labeling that as A. And then this carbon, having been reduced, now has a hydrogen attached to it, so we'll label that as B. But when looking at these 2 hydrogens, we need to look at the molecule 3-dimensionally. We might be tempted to look at them the same way that we looked at them for cyclohexanol, but because this carbon is no longer sp2 hybridized, it is tetrahedral rather than planar, and its orientation is going to affect the 2 hydrogens that we're looking at. So let's give it some three-dimensional orientation, even though this carbon wouldn't be considered a stereocenter because the molecule is symmetric and it has two identical R groups coming off. We need to do this because that group will place these two hydrogens in different chemical environments. One of the hydrogens would be coming out of the screen along with the OH group and would experience a different chemical environment than the other hydrogen that is going into the screen and away from the OH group. We can also look at this compound in the chair conformation and see the same thing, that these two hydrogens are not in the same chemical environment and therefore would not be equivalent, so we call them diastereotopic hydrogens. Now, before further analyzing any other hydrogens, I wanted to go over some topicity terms that will be useful while going over this. I'll start with diastereotopic hydrogens since that's already come up. These are hydrogens that are not equivalent even though they might be attached to the same carbon because they will be in different chemical environments and therefore can produce separate NMR signals if they're unique enough. Sometimes they're still similar enough where we don't see a distinction between their peaks, but we'll still label them differently and we might see two separate signals for them. Usually these hydrogens are attached to the same carbon, although that's not always the case. They could be attached to separate carbons if the carbons are diastereotopic. And when performing the deuterium test, two structures will be produced that are diastereomers of each other. And I'll be showing an example of this in just a second, but let's go over enantiotopic hydrogens first. These hydrogens are basically the opposite of diastereotopic hydrogens. They are equivalent because they will be in the same chemical environment and will produce the same NMR signal. They're usually attached to separate carbons, and when we perform the deuterium test, the two structures produced will be enantiomers of each other. When analyzing these kinds of hydrogens, we have to consider the 3D structure of the molecule. So let's look at this alcohol as an example. And like the cyclohexanol, this carbon wouldn't be considered a stereocenter because the molecule is symmetric, but we had to consider the 3D structure so that we can correctly analyze these two hydrogens. We can see that they are in different chemical environments, so they're probably diastereotopic hydrogens, but to prove that, we'll do the deuterium test by switching out one of the hydrogens with a deuterium, and in doing so, we've created two new stereocenters that we can analyze to see the difference between the hydrogens. Then we'll redraw the molecule, this time switching the other hydrogen with the deuterium, and then ask ourselves, what is the relationship between these two structures? Are they diastereomers, enantiomers, identical structures, or are they just completely different structures? And if that's difficult to answer just by looking at the two structures and maybe rotating the molecules around, then we can analyze these stereocenters to help us figure it out. To do that, we'll label them with R or S values. So if we look at the first one attached to the alcohol, that would be S, and then the other one would also be S. Now we can do the same thing on the other structure. The first stereocenter on the left didn't change, so it would still be S, but the other stereocenter, now that the deuterium is on the other side, would be R. Since only one of the stereocenters changed and not all of them, these two structures would be diastereomers, meaning that the two hydrogens that we've been analyzing would be diastereotopic hydrogens and would not be equivalent. Now that we've figured that out, let's go back to the original structure, and instead of comparing these two hydrogens, let's just look at one of them and see if there is another hydrogen on this molecule that is in the same chemical environment. And because of the symmetry of the molecule, the hydrogen on the opposite side of the alcohol group should be in the same chemical environment. So we could assume that these would be enantiotopic hydrogens, but let's do the deuterium test just to be sure. We'll switch out one of the hydrogens with the deuterium, then redraw the structure, this time switching the other hydrogen with the deuterium. Then we'll ask ourselves the exact same question: what is the relationship between these two structures? And if it's difficult to see that these are two non-superimposable mirror images of each other, then we can label the stereocenters again to help us out. The first stereocenter on the left would still be S, as well as the second one, but on the other structure, the stereocenter attached to the alcohol would now be R because the deuterium is on the opposite side, and then the second stereocenter would also be R. Since all of these stereocenters changed when we switched the deuterium, these two structures would be enantiomers, meaning that the two hydrogens we've been analyzing would be enantiotopic hydrogens and would be equivalent. Now, we can do the same thing for cyclohexanol. We can switch out one of these hydrogens with a deuterium, redraw the structure, and switch the other hydrogen with a deuterium. Then we'll ask ourselves the exact same question: what is the relationship between these two structures? We could rotate the molecules around or even label the stereogenic centers, but in the end, we'd find that these two structures are diastereomers, meaning that the two hydrogens are diastereotopic hydrogens. So we would label them differently and possibly even expect two different NMR signals for the two hydrogens. Now, since this molecule is symmetric, we could look at one of the hydrogens, in this case the axial hydrogen, and look across the ring at the axial hydrogen on the other side, and we would see that they are in the same chemical environment and therefore should be equivalent hydrogens. These would be enantiotopic hydrogens, and we could prove that doing the deuterium test once again. So we'll switch out one of the hydrogens with the deuterium and redraw the structure, this time switching out the other hydrogen with the deuterium. Then we'll ask ourselves the exact same question: what is the relationship between these two structures? We can see that these are enantiomers, meaning that the two hydrogens would be enantiotopic hydrogens and therefore would be equivalent like we thought before. So when labeling the molecule, we wouldn't have to label the hydrogens on the other side of the ring because they are equivalent. Now that we've gone through all that, we can see that there would actually be 8 unique hydrogens on cyclohexanol because the two hydrogens attached to each carbon on the ring would be diastereotopic. So let's go ahead and finish labeling all of the hydrogens. We've already labeled hydrogens A and B, and then we can label all of the axial hydrogens as C, D, and E, and all of the equatorial hydrogens as F, G, and H. Now, if we look back at the H and NMR, you might notice some interesting things. First off, there are only 6 identifiable peaks and 8 unique hydrogens, meaning that there have to be overlapping peaks somewhere. Which makes sense if we look at this peak here. It's really big, has a wide base, and has a much larger integration than any of the other peaks, which means that's where the overlapping peaks have to be. So I would just save that one for the end. After labeling all of the other peaks, whatever hydrogens are left over, they'll just be kind of jumbled up into that one big peak. You'll also notice this box here, which has a reference molecule inside. And it's called a reference molecule because this is a different compound from cyclohexanol. We have a butyl group here instead of an alcohol group. So obviously the chemical shift values given for all of these hydrogens are going to be a little bit different than our product, but we can learn some important things from these values. For example, if we look at these two hydrogens, we can see that the equatorial hydrogen is more deshielded than the axial one attached to the same carbon. And if we look at each pair of hydrogens, we can see that every single time the equatorial one is more deshielded than the axial one. So when analyzing our product, we can assume the same thing will happen, that all of the equatorial hydrogens will be more deshielded than the axial hydrogens attached to the same carbon. Alright, that's all I'm going to go over. I'm going to leave the assigning of the peaks to you, but remember that there are going to be overlapping peaks, that the equatorial hydrogens are going to be more deshielded than their axial partners, and then don't forget to label your solvents as well.